Explain what I mean. For differential fields. So it's going to be an unusual talk probably where all of the audience knows more about the subject than the speaker, because I'm not an expert in differential algebra or differential fields. First time I came across them is when I was proving this theorem. So I'll briefly recall for the setup, what I mean by differential equals field and so on, but you don't need to know much. I don't know much about it. So for me, K will be some, it's a field with an extra derivation, I denote by D. It will be differentially closed. So differentially closed, I guess most of you already know, but it means that it contains solutions to any consistent differential equation that you can write over this field. So for me, I think about something like analytic functions, and you extend them. Whenever you have a differential equation, you extend them with solutions to the differential equation. It's not easy to construct a natural example of these things, which is quite inconvenient for me, but as usual, when you actually do a proof, it's not so important. So when I actually prove something, I really only need a certain set, finite set, or maybe countable set of differential equations to have a solution. And then you can really think about germs of meromorphic functions, some disk or something like that. So my approach is kind of geometric. The proof that I may or may not get to in this talk is geometric, and basically I think that I'm working with analytic objects like meromorphic functions. I'll fix some ambient space, I'll denote it by M. For this talk it will be K to the N. So it could be maybe a risky open subset. Or Zariski open subset. This Zariski open business is not so important. It's kind of a technicality for some of the applications, but basically you can think about just a fine space, K to the N. Again, most of the techniques probably would work for different, you could do it over projective space, over some abelian varieties and so on. It doesn't really matter. Just to make the setup the easiest, I'll do it with a fine space. Just like the regular Bezout theorem, easiest to state in a fine space, and then of course there's generalizations to various ambient manifolds. Okay, so I want to talk about differential equations, to code them in an algebraic language. So the way I do it is as follows. First I'll define a prolongation space of M, ML. It will be just M. So it will be M to the power, K to the power S, where S is N times L plus 1. So I think of this as a space of jets. So again, every element of K, I think about it as a function. Let's say a meromorphic function or something like that. So elements of M would be n tuples of functions, because it's K to the N. And then this ML, it would be for every one function you would have now L plus 1 functions. You can think about it as an L jet, so it's the first L derivatives. And then, okay, the point of defining it like this is that we have a map for taking jets. So if X is a point in my original M, then I will define XL in ML to be the jet. So it will be X dx up to d to the Lx. So it's the jet with respect to this differential operator, which is part of the field structure. Okay, so now with this notation we can say what we mean by an algebraic system of differential equation. Okay, so let's say that y is a subset of ML is Zariski closed. So just defined by the common zeros of some set of polynomials in these coordinates, in the coordinates on ML. Then you can think about it as a differential equation. The coordinates on ML, they're kind of the first, we think about them as the first L derivatives. The function is first L derivative. So if we have some algebraic conditions on this space ML, it basically defines some algebraic conditions on a function and its first L derivatives. So I think about this set as a set of differential algebraic conditions.
Does this depend on the choice of coordinates?
On the choice of coordinates on
ML.
on ML or on M?
Yes, on either.
Well, once you have coordinates on M, you have kind of natural coordinates on ML. If you're making a fine change of coordinates on M, it wouldn't really matter. Otherwise, you need to kind of specify what you mean by change of coordinates on M, because when you do something like Bezout theorem, you want to talk about degrees. If you just take, let's say, an automorphism of a fine space without some conditions, it will not kind of preserve a natural notion of degree. You need to, let's say, you want to talk about degrees, you can talk about projective space. And if you take an automorphism of projective space, then yes, it will not change anything. But an automorphism of projective space will be just a linear automorphism, basically, or a Mobius transformation. So it really depends on kind of what you want to preserve. So I'll say what kind of degrees I want to consider. So maybe let me fix coordinates. So let's say that xc are coordinates on M. So kind of C1 up to N. C1 up to Cn will be coordinates on this M. And then I'll have coordinates kind of C0, 1 up to N. C1, 1 up to N. Up to Cl, 1 up to N. Coordinates on this ML, just in case I want to talk in coordinates. So when I say Zariski closed, I mean kind of it's just a polynomial in these coordinates, where this represents kind of the original functions, this represents their derivatives, and this represents their elf derivatives.
So ML is just the space of those, the jets of elements of F.
No, ML is as I defined it. I mean, it's exactly just K to the S.
Yeah, okay,
it's true that not every element in ML is actually a jet of something. There are some kind of compatibility conditions, so that will play a role in the kind of in studying the problem. So yeah, I mean, if you take the elements of M and take all of their jets, then you get something which has kind of differential algebraic dimension n. But the closure will have dimension, it will be kind of dense in ML, but of course it will not be all of ML. Okay, so anyway, so a Zariski closed set you can think of as a set of differential algebraic conditions. And now I will say that if I have some x's in M, I will say that it's a solution for y if and only if its jet xl lies in y. Okay, so the jet is exactly x and its first derivatives, and then if xl lies in y, then it will exactly mean that kind of this function, this n-tuple of functions satisfies these differential algebraic conditions. Clear? Okay, so basically the question is, so first posed by Hrushevsky and Pila. As far as I know, first posed by them. Hrushevsky and Pila. So suppose that you know that the number of solutions of this y is finite for some reason. So you have a given y and you know that it has a finite number of solutions. then can you explicitly estimate the number? Explicitly estimate the number. Of course, I'm being it's kind of vague on purpose. So what does it mean? Explicitly estimate. Estimate in terms of what? I mean, depends what you know and why, right? I mean, so there could be various ways that you can kind of formulate a precise question out of this. So for example, suppose you know the degree of y, just as an affine variety. So can you estimate the number of solutions in terms of the degree of y? Or suppose you know something about the equations that define y. That's maybe closer to kind of classical Bezout theorem. Let's say you have, I don't know, a certain number of equations of degree d. So can you kind of say how many solutions there will be as a function of d? So there's various ways to make this question precise. Let me start with the theorem that started this business, the theorem of Hrushevsky and Pillai. So Hrushevsky and Pillai gave one kind of answer to this question. There's a theorem of Hrushevsky and Pillai. Theorem Hrushevsky-Pillai, I would say roughly around 2000. Maybe they did it a bit more. It was published around 2000. It says that suppose this number of solutions of y is finite. Then this number is less than or equal to, okay, I'll write it with a squiggly line here. I don't want to give the precise formulation. Something like, something like degree of y to the 2 to the dimension of y.
What is the degree of y in
Okay,
a
so
non-projective setting?
So degree of y, they mean just the intersection with a generic hyperplane. So it would be the same as the degree of just the closure of y in the standard projective space.
Okay.
So I mean degree in this kind of the most naive sense, just number of intersections with a generic hyperplane. Well, this is if y is pure dimensional, then you intersect with a generic hyperplane of complementary dimension. If y has several components, then it's just additive over each of the components. Okay, so this is their result. I want to kind of note a couple of things about it. Kind of, let's say in comparison to a Bezout theorem, there's a good thing about it, which is that it's polynomial in the degree. So Bezout theorem, let's say we have, I don't know, equations of degree d, Cn. If you have n equations, you expect d to the n solutions, right? At the most. That's the upper bound, d to the n. So first of all, it's polynomial in d. And this is also, I mean, okay, here you're looking at the degree of equations, you're looking at the degree of the variety, but anyway, it's polynomial in this degree, which is kind of what we expect. The bad thing is that it's doubly exponential. So Bezout theorem is not doubly exponential, it's singly exponential. In fact, the exponent is precisely n, if you're in dimension n. Here the exponent can be very big, it's 2 to the something. So the growth with the dimension is much worse than Bezout theorem. And also the growth with the degree is a polynomial, but it's not kind of the best that you could hope. You could hope something like d to the ambient dimension. That's Bezout. And here you have d, but to something maybe bigger.
But still with some particular values of d and y, this is a nice number.
Say again?
With some particular values of the dimension of y, this could be a very nice number.
Yeah.
Used in practice.
Yeah, I mean, yeah, if the dimension of y is small, then it will be quite a small number. But yeah, like as a general theorem, it has advantages and disadvantages.
So if the dimension of y is large, then you might want to replace 2 to the dimension of y by just the number of zetas.
Yeah, that would be nice, for
And the
example.
derivative, and the derivative, you know. So this is n times L plus 1?
This S.
Oh, S, right.
S would be an optimal answer, roughly. I mean, that you could hope for. Here you can get something roughly as large as 2 to the S.
It could be smaller, but an exponential, of course, grows faster than just the linear multiplication.
Yes.
It cannot be larger than S.
Right, it should,
Yes.
it should not be.
I mean, it's,
The dimension of Y cannot be larger than S, but 2 to the dimension of Y can
dimension of
still.
Y is a lot.
Yeah, I mean, this can be quite large. Maybe you would hope to replace this thing maybe by S. That would be like
by
a
S, okay.
Bezout theorem.
Yeah,
Okay, so I want to.
But now in the projective setting, of course, that whatever the numbers, it's got to be smaller than what the cardinality would be in projective space.
You're saying that if
Because the point in Kn, in Pn, determines the jet.
Yes.
So the cardinality,
You're saying that if we were to consider it in projective space, cardinality would be larger, possibly? Or I'm
no,
not sure I got the comment.
that would bound, the points there that solve the Y are bounded by the degree
By the degree of Y?
of the intersection,
Intersection between what and what?
Y and the projective space.
No, but I mean, Y is embedded, let's say, in some projective space, but you see, Y can be a positive dimensional variety.
Oh, absolutely, but
It's just that most point of
the
it.
definition of degree says you're intersecting it down, and if the points are determined by, the C naughts, then the issue really it seems is just how many of the C naughts are going to lie in this.
You see, the point is that most of the points in Y, they're not solutions of Y. Solution
Right,
of Y has to be a jet. So
Right, that's what I'm saying. So it has to be in the Pn part.
it has
That
to be
determines it.
Well, I mean, AN is embedded in Pn. I'm now counting only in AN, but N is embedded in Pn.
Yeah.
So, I mean, there isn't much of a difference between the two. But I don't see how it would
So you're
help you
cutting
to
it
count.
down by requiring that the jet should be in Y.
Yes, I mean, I'm considering some specific Y, which is, let's say it's a surface in AN, or it's surface in some a fine space, doesn't matter. But now, most points of this surface, they are not jets of something. They're just points which are not jets.
All I'm saying is that the degree of Y intersected with the Pn is going to bound the number of
why is
solutions.
contained in Pn? I don't understand what you
No,
mean.
it's contained in M in the jet space.
Yeah, so what do you
So
mean
you
by
take its
Pn?
intersection with the Pn, with the zero coordinates. Those are the only places where you could have points whose jets will lie in there.
You mean that you set all derivatives to be
Are you
zero?
thinking about
do you-
projective differential projective space or?
No, I'm
projective
just
space?
using his setup.
But his setup projective space would be an M upper L plus 1.
No, I'm saying the point, this initial point of the jet has to be in the Kn. And I'm thinking if you replace Kn with Pn,
I think what we want to do is not intersect but project, right? You're saying
You're not
take
talking
a
about
solution
if you
and then look at
intersect,
its
then
first
you kind of
coordinate.
only look at coordinates. But
So it probably projects surjectively.
yeah, so it's but that's a bound, that's all I'm saying.
No, you cannot get a bound like that because it would probably
No, the
project
differential equation
surjectively,
did
or
not
it would project to
involve
something
zero
positive
order terms.
dimensional. Maybe not subjectively, but anything.
No, Ray.
Don't worry.
The differential equations, I mean, when you consider them as differential equations, did not involve the zero order terms. Not definitely not, but may
I mean,
not.
definitely may not.
Right. Come on, that's a superfluous word then,
Possible.
right?
Yeah.
So when you're
Okay,
talking about.
maybe we can
may not make
discuss it
sense.
further
Right.
later if we.
Right.
Okay, so I want to kind of state an alternative theorem, but before I do that, I want to remind you of some kind of notation having to do with Newton polytope theory. So I'm going to define if, I don't know, let's say P is a polynomial. P is in, I don't know, P x1 up to, I'm doing kind of classical polytope theory. So if P is a polynomial in n variables, then we define delta P the convex hull contained in R to the n of support of P. Support means that I'm taking all of the kind of exponents that have non-zero coefficients. Okay, so for example, let's say I have P which is x1 plus x2. Then this delta of P will be, okay, I draw R2. There's 2 points in the support. There is kind of x1 is this point, x2 is this point. And then let me add +1 just to make it more interesting. So kind of this will also be in the support.
Why are you looking for Rn and?
Do you want P and R, x1 up to xn?
Yeah.
You have complex on the side and then...
No.
The points have integer coefficients.
Z to the
That's
end will be
right.
fine. In fact.
But the convex, but the convex hull is in Rn.
Yeah, I mean the
The
support
exponent, those are the exponents.
support is in Z to the end. We
And
take a
exponent,
convex hull in Rn.
Yeah.
For some convenient geometric reasons, it's good to consider convex hull in this case.
Yeah.
So and
Those are
then
exponents, right? Yeah.
Yes.
and then this would be the Newton polytope. Right, so is it clear? I don't want to kind of formally define support, but you understand. You take each of the kind of monomials appearing, you draw a point in Z to the n, and then you take convex hull. In fact, you don't have to do it for kind of this ring. You can also allow inverses of x1 up to xn, right? If I do it like that, then it's not really even Z to the n. It's kind of natural numbers to the n. So it's natural to do it for larger rings, but never mind. So this is called the Newton polytope. And kind of a point of this is that there's a theorem. We call it BKK. So it's Bernstein, Kushnirenko, and Khovansky. Says that if, so again, I'm in this setting, so I mean my p's are in just n variables. So if I have p1 up to pn in this polynomial ring, x1 up to xn, and delta of pi is contained in delta, so I have one delta which contains all of these, the Newton polytopes of all of these n polynomials. Then number of isolated solutions of the system P1 equals Pn equals 0 is less than or equal to n factorial times the volume of this delta. So this is kind of an extension of the classical Bezout theorem. If you want Bezout theorem, you just take delta to be kind of the standard n simplex. So Bezout would be taking delta, which is, I guess, d times kind of the standard d simplex. So d0 is the convex hull of, well, I don't want to write, it's the standard, d0 is standard n simplex. I mean, in the Bezout theorem, you want to say that just all equations have degree d. So it's the same as saying that this Newton polytope has a certain shape. It's kind of just you allow yourself up to d in each of the coordinates, and you take convex hull, and this way you get the Bezout theorem. So this is more general, and in fact, it's quite tight. So this theorem, if you take kind of generic equations with the given Newton polytope, let's say you have a Newton polytope delta, which is a convex hull of some set in Zn. And now you take some generic equations with this given Newton polytope, then this bound will be precise. So it will have exactly this many solutions. So this is a very good bound for this kind of setting. There's also in fact, what I showed now is maybe just the Kushnirenko theorem. So the general theorem also involves the case of what happens if you want to prescribe a different polytope for each of the equations. Right, so here I just fixed one polytope delta, and I said all of them have this polytope, all of them are contained in this particular delta. You can say, well, what if I fix one polytope for one, another polytope for another, and how many answers will I have? Again, there is kind of a very tight bound. It involves some kind of a multilinear extension of this volume function. It's called mixed volume, a very important function in convex geometry, but I just don't want to get into it. So whatever I say, I'll talk about this case with volumes, and it can be extended to kind of cover different Newton polytopes with mixed volumes. If you're interested, you can see my paper. So now I want to kind of give a version of this bound for a number of solutions of differential equations in terms of Newton polytopes. So we state the theorem. So suppose that y is cut out by equations with polytope delta. Now, just to remind, this delta now will be in R to the S, right? Because we're talking about equations defining this y. It's kind of equations involving the function and its first L derivative. So I take Newton polytopes in this.
When you say many equations, one polytope, do you mean the same thing here? That
yeah, I mean that they all have, they're all actually contained in this polytope.
Delta could be just the convex hull of all the supports union.
Yes, yeah. Basically, if you just have some equations, the best thing you can do is take all of the supports, take the convex hull, and then kind of you'll take this delta and get some bound that I will write now. So I just want to say it's slightly different from the Hrushevsky-Pillai theorem that I mentioned before, because before I was talking about the degree of y, now I'm talking about degree of equations. So degree of equations may be usually a bit smaller than the degree of y itself. But you have several equations, then degree of y will be a bit bigger. So just keep in mind that it's kind of slightly different data that I'm working with here.
It could be exponentially bigger.
Could be, yeah, the degree of y could be exponentially bigger than the degree of the equations. Usually it will be, let's say, if y is complete intersection or something, close to a complete intersection, certainly. Okay, now suppose, as before, that the number of solutions of y is finite. Then this number is less than or equal to some constant C n L times the volume of delta. And this C n L, I will not write it precisely, but it's exponential in n and L. So it's not double exponential, it's... I have, in the paper there is an explicit form. It's something like, let's say, 2 to the n times L squared or something like that. I don't want to confuse you with constants, but the point is it's single exponential, whereas this Hrushevsky-Pillai result, it could be double exponential, right? We could see some degree to the 2 to the dimension. So if you just kind of fix all the degrees and think what happens when I increase dimension, it could be 2 to the 2 to the n. So here you don't have it. This guy behaves like 2 to the n or 2 to the n squared. And then you have the volume. Now the volume is kind of almost optimal. So before I talked about what happens with respect to the degree. Let's say I fix some dimension and I look at equations of a given degree and I see what kind of bound can I get. Well, then this volume is essentially the best that you can get. For example, if your equations are all of degree d, then this volume will be something like d to the s. Right? And s is the ambient dimension. I mean, volume grows like something to the dimension of the space. Right? If you take a volume of, I don't know, a d-dimensional cube in S space, it will be d to the s. So these are the two kind of directions of improvement. One is with respect to these parameters n and l, where it becomes single exponential. The other is with respect to the degrees, where it becomes kind of tight, so asymptotically tight.
And so I have a question. So have you compared your bound with the bound of Hrushevsky and Pillay for a small number, small dim y? So is there other cases in which their bounds are better than yours?
I mean, it depends on because the data is slightly different. It's hard to say. So if you have a y where it's not given by equations, so let's say you just have a y, kind of you're given abstractly a y of a given degree, and then you try to do the bound, then it would be hard to compare, because for my result you would need to find equations.
But for concrete equations, so if you have concrete equations.
Again, if you have concrete equations, the question is, do you assume what do you assume about the degree of y? Maybe you have a concrete equations for y, but it's not a complete intersection. So the degree of y could be much smaller than the product of the degrees of the equations. So you see, it's kind of...
But my question was, are there examples in which their bound is better than yours?
So the answer is it's difficult to compare. If you are just given an abstract, let's say you're given y, which is an abstract curve, and you don't know any equations for it, you have to use some machinery to find equations. Then maybe you will not find equations of very good degrees.
No, he's asking, I think, that can you give a concrete example where you know both the equations and the degree of y? Where then the bound
where I know when I know the best degree, kind of the best equations for y, and I know the degrees of y, and their bound. I'm not sure. It would be hard to construct. What I can say is that kind of in all the cases that I know, usually you have a y which is given by equations, and you kind of bound the degree of y in terms of these equations. And in this case, then this result is always better, kind of considerably better. I cannot say that there cannot. I mean, in the general case, it's kind of it comes to kind of delicate questions of comparing the degree of y to the degree of the equations. Questions about curves which are kind of highly far from being complete intersections. I'm not sure. I thought about it a little bit. There is some kind of technology for finding low-degree equations for a given variety using Hilbert functions, and I would say that I can always get close with this result to their result. I'm not sure if really this result is always better, but I didn't think too much about it because I don't know any examples where it's really interesting. So in all the examples that I see in the literature, you have a y and you know the degree because you know something about the equations of y. And then and in these cases, it's built in such a way that this will have to be better than that. I mean, that this result will be better. If you have equations for y and you're bounding the degree of y in terms of these degrees of the equation, then certainly this result will always be better. Okay, so I want to give some motivation for why Hrushevsky and Pillay consider this problem and why I considered it later. So the motivations involve some application, some kind of Diophantine applications that Hrushevsky and Pillay found.
Is there any way to estimate the dimension of y or the degree of y given L?
To estimate the dimension of y? Well, dimension of y, do you mean the algebraic dimension?
Well, that's what you mean, right?
But I mean, y is just a variety. So what do you mean estimate the dimension? Estimate in terms of what?
Oh, well, of course, S is an estimate.
Yeah, I mean, so in general it could be S, but in some cases maybe it's smaller. Maybe you know that you come to some y which is something, you know something about that y. So, for example, a common application is that you start with a curve, then you consider its L prolongation. So the L prolongation of the curve will have dimension L, or maybe L+1. So this dimension of y will be something like L. And L would also be a parameter of the problem. So that's one of the examples maybe that I will show. But okay, let me kind of explain what is the motivation. It's a very nice result of Hrushevsky and Pillay again. So for this motivation, we are kind of in the same context in a differentially closed field, but I'll kind of fix more concretely K to be the field of complex numbers, which is kind of mysterious for me. I don't know, maybe for people who work in differential algebra, it's a normal thing to do, but okay. Now we have K, which is the complex numbers. We know that it's a field.
I just still want to understand a little bit more. About the Hushowski-Pillay bound, L is not explicitly written there.
It's not explicitly written there,
So that means that it is true for any L. Is that correct then?
yes, but you see, because the y
But
is...
then the Y changes.
Yes, the y
The
changes.
Y changes. Okay.
L is the orders of equations.
Well, for
you-
example,
Yeah.
I guess if you...
So as you keep prolonging, then the dimension of Y keep changing, and it
Yeah.
Yes.
increases.
Yeah.
Yes, I mean, if you just...
But why is given?
Y is given. It's not the Y, it's the...
Right, yeah.
Oh, that's right. Then the number
Yeah.
N is also
Yeah.
depending on that.
Yes,
on
it's
L.
given by a customer.
Yeah.
Y is given in some space which depends on both n and l. So,
Right.
you, for example, you might know from the beginning that y is just zero-dimensional. Then it's very easy to estimate, right? I mean, then it just has points.
That's good. So in other words, in Hushowski-Pillay's theorem, as it's stated, it really should say the number. The number is as a function of L, n and L. At the same time as Y as a function of n and L.
I mean, the number depends on y.
Right.
Y kind of, as it's given, it's already depending on n and l. I mean, it's kind of a subset of something depending on n and l.
Okay.
William, so that statement of
fine.
Hushowski-Pillay theorem should be read together with the first word that was erased here, not by independently. So it was a setup. I mean, everything was introduced, N, L, and so on. What they
No. See, what
by
I'm
itself,
thinking is about the growth as L increases, because I am interested really in a differential solution, not a jet solution. Right? So I'd like to know how this number that you're estimating actually changed.
Well, so to think about how it's going to change as
Now,
you
it
prolong
should- it should
L,
go
you need to prolong
It
Y.
should be smaller and smaller, right?
Well, so
Because you put in more and more condition.
Yeah, but then you need to say what more. I mean, y is given. So if you consider bigger L, you should.
but Y is given. Y could be given as coming actually from a differential system of equations.
yes, so
Yes,
of
but-
low order.
so
Low
William, I
order.
think what you're asking.
Then the L is exactly this order. If y is given
Yeah,
by a
so-
system of differential equations of order 3,
So I think
then
here's what-
everything happens in kind of L equals to 3.
I think-
L is exactly the order.
No, that's
I
not
think-
that's
wait,
not
wait,
what
wait.
is meant by
I think-
solving the differential equation.
I think here's what William is actually asking. He's saying, start with a particular y and a particular L. Now consider prolongations of y to higher spaces. Now you have a sequence of varieties,
Exactly.
y sub L, y sub L plus 1, y sub L plus 17. And what he's asking is, how does the number of these solutions vary in this
I
family?
don't understand what it. I don't understand. I don't understand what it means. Why
number
is
of jet solutions.
why is
Could you
just a
explain why you
system
want
of
to ask this question?
Because I want to actually solve a system of differential equations,
but-
not an algebraic system and try to find jet solutions.
He does it with his
No,
mouth.
that's exactly what I do. I have just a system of differential equations, a system involving
Right.
functions and their derivatives.
No, but you only want to satisfy the equation up to the order of the equation.
No. I have a system of equations. There is I have this what I denoted by XL. It's the L jet, but in the differential algebraic it's x dx. It's the function. Its derivative
Right.
dlx.
Yeah.
Now, when you say that this satisfies some algebraic condition, it means that x satisfies the algebraic equation completely. It's not.
Yes,
it's not x.
but the d sub L plus 1 would not satisfy the equations.
No.
What do you mean no?
This would be true if it was x evaluated at a point. This is not this thing evaluated at some point. That would be kind of a classical. This is just kind of the tuple of the function. It's if I write an equation like c equals c1, and this x satisfies it, it would mean that x is just equal to dx. That's what this would mean.
Yeah, but as a differential equation,
X as a
But
differential
now
equation.
you
As a
take
differential
L equals
equation.
to 2.
Equation.
What do you say? Now look at
dx.
L equals 2. That equation, you have to extend
Solutions
it.
to this would be functions satisfying x is equal to dx. That would be only exponential functions.
okay.
Okay, it would be if it was kind of x evaluated at 0 is equal to dx evaluated at 0, then I think that's what you're asking about. But that's not what I'm talking about. I'm saying that the function is equal to its derivative. So it's exactly solutions to system of differential equations. Just an algebraic way to code it.
All right. Okay.
Yes.
Are you distinguishing between jet solutions and non-jet solutions?
No, for me, solutions are always functions. They're elements of so they cannot be jets. They have to be functions.
Are you looking at all solutions or solutions of that form?
I'm looking for solutions X.
Solutions of that form,
Yes.
X, dx, etc.?
Yes. Yes, that's what he defined the solution
No,
to be at the beginning.
no. It's not what I define the solution to be a point in the original space, just the X, such that XL satisfies the conditions.
Yeah.
So solutions would be just any n tuple of functions,
So
such that when you look at it and its
differential
derivatives, then they satisfy.
Yeah.
So
Closed field.
it's really exactly kind of systems of differential equations,
my question.
just an algebraic
Because
language
you
for
also have
coding.
non-differential
No, from the
solutions
equation x equals
to
dx,
Yes.
any set of
I would
differential
have
equations, so
dx
that
equals
don't
d squared
satisfy
x,
dx, etc.
right?
Yeah.
In other words, they're just
Yeah.
variables.
Right, I would have
and they're
dx
just
equals d.
Yeah, but okay, so but
Okay,
he's talking
but
about the solutions
I might have
as a system of differential
a
equations.
function x
Of the original differential.
where x
Yeah.
equals dx,
An element
but
of
not-
differential equations.
No, you cannot have it.
no,
If it's
no, for this example, no, of course, for this example,
it
as
satisfies
we know.
and
But in
in
general,
any-
how
in
do
any-
you know?
What do you mean? In any, I'm considering functions that
So
satisfy this system of. You're just saying from this differential condition, other differential conditions
okay,
follow.
you allow. Okay,
You would have an infinite set, but
sorry.
there would only be a finite
I mean,
number
it's
of
kind of.
dx.
Maybe you need to get used to the
Okay, I'm
notation a
sorry.
bit,
Yeah.
but really, it's I'm kind of just
the actual
saying that the function is derivative satisfies some algebraic conditions. That's all. I mean, it's kind of.
Differential solution.
Yes.
But there
Okay.
could be lots,
I think
an
that-
infinite
Yes, of
number
course.
of.
Yes.
I think that as well.
Yeah, we can continue discussing.
Yeah,
it.
that's not-
There
Yeah.
could be no differential solutions, but
Yes.
it's
Okay.
many algebraic.
Let's continue.
Something
Okay.
still unclear?
No, that's
Any other
No, I
questions?
think all is good.
Okay.
With the,
Oh, feel free. I mean, we have time.
we're
I
happy.
mean, it's a long. Okay, so for this motivation, we take k, which is equal to c, and we need to. Okay, it's clear what is c, it's just not clear what is the differential. So differential will be chosen.
It's not quite clear what C is. But never mind.
Well, for me, I don't know, I'm a geometer. For me, C is kind of. I'm very happy to work with C, but I don't understand how to put D on it. So we choose D such that the. Okay, let me call it K0, the constant, which is the kernel of D, is going to be Q bar, so algebraic numbers, closure of Q. So it can be done, because Q bar is some algebraically closed field. Then you can start making differential extensions of it, while keeping Q bar to be the only constant. And you kind of need to do it again and again, maybe C times, where C is the cardinality of the continuum. So it's kind of a highly bizarre object. Probably you have to use axiom of choice to build it, I guess. Nonetheless, it can be done. So, I mean, doing this, although it's very strange for me, it's a kind of a powerful idea that I think originates in the works of Bouillon. So he used it kind of to prove very deep results, like a geometric line conjecture and other results.
I don't think he actually was
And
central.
Khrushchevsky and Pillai kind of also work in this context. It's a context which is convenient for model theoretical considerations. So, okay, so that will be our context.
Genetic derivations, then.
Questions? Comments? Okay, so now I want to show a theorem of Khrushchevsky and Pillai that uses this setup. So this is a theorem, I'll call it theorem 1. Khrushchevsky and Pillai. It's kind of in the same paper where they proved this, the bound that I'm talking about. Kind of the goal was to prove this following theorem. So, yeah, I want to get everything right. So let x in c to the n, or you know what, I'm going to, let me fix first another notation. So I fix what k is, let me say also what m is. I take m to be c star to the n. So before I took just c to the n, but I said actually you can take a Zariski open subset. So now I want to take a Zariski open subset. C star means I drop 0. The reason is that we want a group. So I'm taking the simplest possible group, the torus group. in fact, this theorem holds for other group. It holds for tori, it holds for abelian varieties, and it holds for what's called semi-abelian variety, which is a product of a torus and an abelian variety. But I mean, really, you can get everything from the toe. So the theorem is kind of the same, even if you want to do it more generally, just you replace this M by more general M. Okay, so now, I'll state this theorem 1 of Hrushevsky and Pillai. So I take X, which is a subset of M, defined over Q bar. So it's an algebraic variety defined over algebraic numbers.
Now, actually, I think a source of confusion here, something was of mine. M, the way you've been thinking of it as functions,
Yes.
not as points. And the usual notation is k to the n are the points. And here, so M, now you're thinking of this as functions. So you're really thinking of this as n tuples of functions.
The elements of K n.
It's different notation. All I'm doing is alerting you that the notation you introduced is what led to, I think, to confusion.
But I'm not sure what kind of. So I'm doing kind of algebraic geometry over
Right.
K.
So what you would do is you write M equals
K to the n.
No, functions on k to the n.
No. But no.
No, because the standard definition of affine n space is k to the n.
Yes, but it's in
That's
affine n
K to the
space
n.
over
That-
the theorem.
And k to the
So the
n.
K is the function.
But that's what I'm saying.
let me just-
Your notation is what caused problems, I think.
Well, it's okay.
I'm not sure how to. I feel
It's just I have a semi-movement.
let me give you an example.
Enough. Go on.
You know.
No, I just
Go on.
I don't want to cause a confusion. For example, let's say you consider a
I'm
field
not
of
confused
rational
anymore.
functions.
No.
Well, anyway.
Are these constant? Sorry, I should have said anything. I should have said anything.
No, I mean it's a.
No, go ahead.
It's
Go
an
ahead.
interesting
Please, go
discussion,
ahead.
But
Go
really,
ahead.
a good way to think about these varieties defined over Kn is something like it's a family of varieties, right? Just like when you're doing algebraic geometry over, let's say, a field of rational functions, over CT, you should be thinking that you're working with a family, kind of where T is an extra parameter, but looking over a generic point, right? Because elements of CT might not be defined somewhere or something. Really, it's kind of similar. Elements of K, they're kind of functions. You should think that you have a family parameterized by kind of something, and you're looking at a generic point of a family. It's kind of doing algebraic geometry over a function field. Which is slightly confusing in terms of dimension. So kind of you maybe imagine a family, kind of you kind of go one dimension higher when you imagine a family. But anyway, never mind. So now we're taking X, which is defined over Q bar, and I want to add one more assumption to it, which would be nice to remove, but Hrushevsky and Pillai unfortunately needed it. So I'll be assuming that for any x1, x2 in X positive dimensional subvarieties, x1 plus x2, now these are varieties, right, not points, is not in X. So it means that this X is kind of quite far from being a subgroup. This plus is, the plus, this is an abelian group. When I write plus abelian group, okay. Maybe I better denote it by times, because, I don't know, in C-star the operation is multiple, but never mind, it's the group operation. So we're saying it's quite far from being a subgroup. In fact, you cannot even find two curves inside it, such that when you add them up, they will still lie inside. So it's very unclosed under addition. And there are interesting conjectures about relaxing this condition. But anyway, suppose that we have this condition, then... Oh, I forgot to make one more notation, so let me add it here already.
That's a multiplicative.
Well, you just said that. You said you could use times.
Yeah, it's just, it's the group.
Slow writer.
I'm sorry, yeah, it's just the group structure.
So that's bad for me, I have to.
Maybe I better write times here.
Yeah.
Yeah, it's because see I'm following their notation and then they do it for general
That's right.
abelian varieties. So they just anyway, yeah.
But multiplicative group.
Multiplicative group. So I'm just adding some notation here because I forgot to make them there. So I'll also take gamma in this C star to the n. A finitely generated lattice, finitely generated subgroup with R generators. So, in fact, instead of saying finitely generated with R generators, we could say of rational rank R. So you can also allow torsion points. I just don't want to get into technicality, so a good way to get an overview for what the theorem says is just to think about, you take some R points in the torus and you generate from them kind of a group, a lattice. And the question that Hrushevsky and Pillai are studying and that Bouillon studied before using similar tools is how to understand the interaction between the geometry on this group, on this lattice, and kind of algebraic geometry in the ambient space. So there's the Manin-Mumford conjecture, there's various conjectures that talk about how kind of these two geometries interact. So, and this Hrushevsky-Pillai theorem that I state now is kind of gives you some effective understanding of this interaction under this admittedly annoying assumption. So if you have this assumption, then the number of points in X intersect gamma minus x q bar. So I'm taking intersection points between x and gamma, but I'm not counting algebraic points. Counting algebraic points is a different matter. It's more of an arithmetic question. These tools don't really deal with that. But suppose we don't want to count the really algebraic points of x. For example, if x is a curve of genus greater than 1, then probably there's only finitely many you can maybe deal with these algebraic points by different methods. It's a kind of classical subject of algebraic geometry. So here we are studying a different kind of question. We're looking at lattice points which are not algebraic. Then this will be less than or equal to, let me get it, the bounds right. It's something like, again, I'll do it with the squiggly line, degree of x to the 2 to the n times r.
Yeah.
Okay, so you can see that it's quite similar to what we saw before. And right, you have the degree of x here, and then it's 2 to the something, and this something will actually be an ambient dimension of some system of differential equations that we will construct. So kind of this theorem is, okay, according to the theorem, actually it's kind of a corollary, which is quite, the active part is quite corollary from Hrushevsky-Pillai. Kind of the interesting bit is how do you construct a system of differential equations with finitely many solutions. Then it's very easy to count them just using this Hrushevsky-Pillai result. So I want to give a proof sketch. I cannot really give a proof. I can't say that I completely understand the proof, but a proof sketch. Just to kind of show how these two worlds connect, so how it comes from this very discrete looking thing. We have kind of finitely generated subgroup to some differential equations or something. So that's the interesting part for me. So I'll start by kind of defining this logarithmic derivative, log derivative, because we're in the torus, it's extremely easy to define. So the logarithmic derivative of x will be equal to d of x over x.
So here you're moving to the first prolongation, or?
Right now I'm just defining an operator. To write the system of equations, I'll say which prolongation I need. But now I'm just defining an operator. I'm saying,
Well, what is X? Is X a Zariski closed subset?
No, little x. That's little x there.
oh, I'm sorry, yeah, this is little x.
Yeah.
Yeah, this is that x is big
No,
x.
no,
It's
no, that's not my question. Is that when you say defined over Q?
yeah,
Is that
I
Zariski
mean,
closed?
yes, I'm sorry. I mean a variety. I mean a
Variety.
Zariski variety.
And so you can prolong it, whatever.
Yeah. Although I mean, doesn't really come into the picture, this
I was
prolongation.
wondering what
right
dx
now.
meant within the context of
This x and that x
itself.
are different
Yeah,
things.
but here it's kind of a small x. This is just a now
Small x and a-
What
an
does
element.
dx mean if you're sticking right?
So
in
this
C star
LD,
to the-
it's kind of from M
Oh,
to Kn. So it just takes the torus, and then every point. I mean, a torus is kind of an n tuple of points. A point in the torus is an n tuple of points. I take each of the points, I take a derivative, and I divide by the point.
well, that I'm used to.
Yeah.
but in this context, I'm confused about you don't remain in zero order. You're moving to first order
What do you mean?
in your context.
I'm just defining an operator. I didn't. I mean,
so
I'm
This x is not that
dx
x.
is in C.
K.
In
It's
C.
in K.
C, yes.
C.
Yes.
Yes, it's
X
also in
and
C.
C.
I mean, my K in
K,
C, and so D takes C to C because I mean my K is a differential field. So yes.
Okay.
So and then this again will be in C.
Yeah, that is fine.
Okay. Yeah, maybe just
Yeah,
not to confuse you. I write here C to the M, not K to the M. C to the M. Because K is C. Okay, so that's a logarithmic derivative. The good thing about logarithmic derivative is that it takes kind of our group law, this multiplicative, we're in the torus, we have a multiplicative group law, and it takes this multiplicative group law to an additive group law on Cn. Right?
The problem I have is that here, when you read this theorem, you remain in algebraic geometry. And you're talking
when
about
you read-
Zariski topology
when you read this theorem,
and rational functions
yes.
not involving derivatives. But when you write that, you're moving from algebraic geometry to differential algebraic geometry.
But that's
Now
why
we're used to it.
This is why math is beautiful. I mean, this is a theorem. It looks like a theorem just about Zariski closed sets and their interactions with lattices.
Yeah.
In fact, in order to study this theorem,
Okay.
like we will construct some system of differential equations, which will indeed involve some derivatives. So you don't see derivatives here. That's why it's surprising that derivatives will come up in the proof, and they do. I mean, so like that's the.
Not only they do, but this D is particularly constructed to satisfy that condition.
Yes.
It's not arbitrary D that you give.
No, you need a D like this.
So you have
So.
a derivative.
So indeed, here there are no differential equations, and
I see,
differential
yeah.
equations kind of will pop up in
this
the proof.
construction, you don't leave C.
So,
Right.
Yeah.
okay, so the main thing about this logarithmic derivative is that it takes, okay, we know that logarithmic derivative takes products to sums, right? I mean, that's we learn in, I don't know, high school or something. So it still works here, right? It's a completely formal consequence of Leibniz rule that logarithmic derivatives takes products to sum. So it means that LD of gamma, if let's say we take this LD and we apply it to every element of gamma, so this will be a space, finite dimensional Q vector space. Right, because it's basically, in fact, it's even more. It's just a finitely generated additive group. Finitely generated additive group is certainly of finite dimension over Q. If you just take the Q span of these logarithmic derivatives of the generators of gamma, then they will be a Q vector basis for this LD of gamma. Is it clear? So that's kind of, I don't know, the key insight why Bouillon started to use them and why Hrushevsky used them in his book.
Yeah.
They kind of allow you to take a very complicated object, like a multiplicative subgroup of the torus, and after applying logarithmic derivatives, become a very simple object, something like Q vector space, finite dimensions, so easy to work with. And a similar thing holds for other abelian varieties. So there is It's not such an easy logarithmic derivative to construct, but there is some extension of the logarithmic derivative which satisfies similar properties. So that's why I restricted the torus. It's easy to kind of say exactly what we're considering and just using high school algebra.
Why is it a Q vector space?
So
If gamma is a finite generated subgroup.
yeah, you're right.
Contained in.
I'm a bit. It's kind of, let's say it's contained in a finite limit. You're right. I'm a bit loose here.